I just want to say that was an absolutely brilliant presentation, and I would have happily sacrificed my time to listen to you more. Absolutely. So my name is Isabella Cooper. I am a biochemistry and pathophysiology scientist at the University of Westminster. And today I'm going to be talking about the details needed to conduct high-quality ketogenic metabolic trials. And then also, beyond glucose, fueling cancer cells, the growth factors. So how ketogenic metabolic therapy actually can influence growth factors that actually stimulate the cells to grow and divide, and actually are the ones that are also driving the inhibition for controlled cell death. So I'd like to thank you. Oh, wait, there is a missing slide. No, okay, sorry, no, this one. So the first is I would like to thank my co-authors, the team, everyone. Not possible to have conducted this research, and quite a fair few of them are here today. So one person can't do all of this. And then also to declare that I have no conflicts of interest, and the research that we conducted that I'm going to be talking about today had full ethics approval from the University of Westminster. So, current data, as everyone knows, is that metabolic dysregulation is increasing. And I think that it's really important to pay attention to it's not just obesity. That's a really obvious way to know that there's metabolic dysregulation, but there are lean people who have metabolic dysregulation as well. And to only assume that it's obesity is a disservice to lean people and then missing earlier detection. Metabolic dysregulation can also be called hyperinsulinemia, in actual fact, because we talk a lot about the glucose, but the glucose is actually stimulating too much insulin for the individual. So hyperinsulinemia currently, unfortunately, is usually only picked up when the insulin levels really are outside of the reference range. But in actual fact, individually, hyperinsulinemia is different for each person. So you could, a very low level of insulin for one person can be perfectly fine, but what looks like a low level for another person isn't. And the way that you can actually detect that, there are multiple ways, but one of them is actually testing the presence of ketones at nutritional levels and above. And chronic levels of hypoketonemia, so low levels of ketones, is a way to know that your insulin is probably too high for you. And the best way to do that is actually not a morning test. Morning tests are valuable, very informative, good to do. But in terms of knowing if you are hypoketonic and therefore likely to be on that spectrum of hyperinsulinemia, is actually to test just before dinner or just before you go to sleep, at least 3 hours after a meal. And then you do this for many days, ideally at least 7 days. And if your ketones are below 0.4 consistently at that later part of the day, 3 hours post a meal, then your insulin is likely running a bit too high for you. And we're going to get into the reasons why. So hyperinsulinemia, chronic excess insulin, is one of these things that increases harm to mitochondria, increases reactive oxygen species, and it does this via increasing the production of ceramides. And these ceramides then increase the reactive oxygen species at the mitochondria. And this research was basically done by Dr. Ben Bickman. Amazing research. I encourage everyone to go and read. And so the ceramides increase these reactive oxygen species that harm the mitochondrial membranes, the cristae, the cardiolipins, special fatty acids that are inside of the mitochondria that are fundamental to the oxidative phosphorylation machinery. And as that cardiolipin is damaged, then the mitochondrial behavior changes. There's crystolysis, there's less OXPHOS capacity. And the mitochondria start to send out these reactive oxygen species signals that tell the cell to grow and divide. So in the most basic, simple way, you see the signals that are coming in. These are the two pathways, the dominant ones, PI3K, MAP kinase. And the signal from the mitochondria is to grow, divide, proliferate, and at the same time inhibit the driver of healthy controlled cell death, healthy, controlled demolition of cells that are no longer good and fit for purpose. So in order to remain healthy and alive for a long time, it's not for the same cells to be there all the time. They've got to repair themselves. And when they're not functioning, when they're not fit for purpose, cells have to go through this controlled cell death mechanism called apoptosis. Additional to the issue with the hyperinsulinemia, hypoketonemia, which is primarily driven by excess consumption of carbohydrates. So anything that's going to be raising your blood glucose. So of course, we talk about the excess consumption of carbohydrates that will raise blood glucose. But of course, we know that steroids will raise blood glucose. Radiation will raise blood glucose. A lack of sleep will raise blood glucose. So it's more than just the diet, but the diet plays one of the biggest roles in it. That raised blood glucose then increases insulin demand in your body. It makes you produce more insulin. And insulin is the king and queen of all the growth factors. It controls all the growth factors afterwards. And we know in cancer research, there's all these inhibitors or, antibodies against the growth factor, ways that they can block that receptor on, vascular endothelial growth factor or endothelial growth factor. Are you ER positive, receptor positive, endothelial growth factor receptor positive, all these sort of drugs that are trying to develop these inhibitions of these pathways, but they're not looking at, well, what's regulating these receptors? What's making more of the growth factors as well? And why aren't those inhibitors working very well? Well, it turns out insulin can often activate those receptors, and each of the growth factors can cross-activate each other's receptors. So the origination of this trial that I'm going to talk about that we conducted was not in cancer patients. It was to provide the healthy control group. Because in actual fact, every time when I was studying and I was reading lots about ketogenic metabolic therapy and trials, they were in diseased cohorts, which was necessary and fascinating, but or they were in high performance athletes. And I thought, there's really nothing on people who've never been diseased, who are not high performance athletes, because I'm certainly not one of them. So, that's sort of, it's not necessarily translatable. And then I thought, well, we probably evolved actually most of the time, actually more of our time in ketosis, because if you have to explain everything in the context of evolution, we wouldn't have necessarily had 3 square meals a day, we wouldn't have had snacks in between. And so under the understanding that we likely spent more of our hours in ketosis, then shouldn't we study those people who just sort of live their life mostly in ketosis and therefore not hyperinsulinemic? And so I wanted to study them and then introduce the fad diet, which is the carbohydrate diet that blocks the ketogenesis, and have a look at what happens. And, we wanted to address a few other kind of questions as well, the usual sort of thing, it's not sustainable. And I happen to know quite a few people who've been living their lives in ketosis for many, many, many years. And I thought, well, if it's not sustainable, how are they sustaining it? And you often hear it's not for regular everyday people, it's only for epilepsy. And I just thought, well, again, that doesn't make sense for evolution either. The usual sort of things, well, mainly with cancer, it'll cause cachexia. It's really bad for you. And I thought, well, babies are often in ketosis and they grow. I've been to the Serengeti, seen and met the Maasai, and, there's research on them too. And they're not eating a heavy carbohydrate diet. They're pretty tall. The research on the Inuits, all these sort of things. And, you can get into the argument of what level of ketosis they're in. But, I think that when we look at high levels therapeutic ketosis for cancer, that's because there's a condition of cancer. People who are healthy, have no health conditions, then there's going to be different degrees of ketosis that they're going to be in and the necessity for it. So we conducted this trial in women as well. Partly because of the reason that women are quite understudied, and when they are studied, they're usually studied in the postmenopausal state, or if they're premenopausal, then usually they're put onto birth control hormones, and so realistically that's not natural physiology, and we need to understand these things in the context of natural physiology. In this trial, there were 10 healthy women, and we originally conducted a pilot trial beforehand in order to do a power calculation, meaning how many do we need to conduct in order for this trial to be fully powered. And the final calculation from our pilot was actually 9 people. So we conducted on 10 in case we would lose a participant, which we didn't. So these participants, the group average was 4 years of being in ketosis and quite high ketosis. But we didn't take their word for it. This is a thing, so we had them test their capillary glucose and ketones for 6 months. And it was the pre-dinner test or pre-going to sleep test, and it was 3 hours post any meal. And they had to demonstrate that they were in nutritional ketosis. So that's above 0.5. In actual fact, our cohort participants, they were typically in really therapeutic levels. Then the trial phase itself was actually 66 days long, divided into 3 phases. Each phase 21 days. And at the end of 21 days, they come into our lab and they come for blood tests and anthropometrics. And, we subjected them to oral glucose tolerance tests. And so the 3 phases, essentially the first phase was a baseline phase. It was to actually study them in the way of their own lifestyle. And the second phase was the intervention phase, when we had them suppress ketosis by following the UK Eat Well guidelines. So that was to consume 267, no less than. So they encourage more, 267 grams of carbohydrates a day, split over 3 meals a day and snacks in between. That's the healthy recommendation. So that's what we did. And it definitely does suppress ketosis. And then they came into the lab. And then in the third phase, they actually went back to their normal lifestyle, which was to be in ketosis. And this was for us to understand any changes that we might see. Was it because of the intervention? Or was it because, we were at that time with a lot of the participants, the way the timing of each section of the trial was for the participants, we were moving into winter. So who knows, maybe it was a seasonal change. So we wanted to have that third phase in order to understand really how much of that intervention was really having the cause of the changes that we saw. And then for compliance, and this is really important in trials, and especially cancer trials, because I read a lot of them where they test ketones in the morning, and usually it's urinary or breath ketones, urinary being the most common. But the problem with that, and the published trials, is they'll have this compliance of you have to be above 0.5 in order to be classed that you're maintaining ketosis, which, a lot of you will understand, for cancer, that's too low. It's actually too low. And so if you're only measuring this in the morning at 0.5, and you have a metabolic disease condition, it's likely your morning coffee with a bit of milk in it is going to knock you out of ketosis. You don't actually know if your breakfast, if your lunch, if your dinner, if your stressful job, any of these sort of things are actually going to be putting you out of ketosis throughout the day. So in a lot of trials, you get this false positive confirmation that the participants are actually maintaining good levels of ketosis. And I will but say something else. Ketosis without taking exogenous ketones, without taking MCT, is important when it comes to understanding, are you endogenously producing these ketones? I'm not saying don't take exogenous ketones or MCT oil, but you need to understand what helps you get into therapeutic ketosis without that extra outside help, because it's about the insulin harming the mitochondria and the insulin increasing the growth factors. So, if you have a blood glucose of 5 and you drink a whole load of ketones, and you get your ketones to a level of 5, you've got a GKI of 1. But by not avoiding eating the carbohydrates, you didn't actually lower the insulin. So you didn't lower the assault to the mitochondria. You didn't lower the signaling of the grow, divide, proliferate, and inhibit controlled healthy cell death. So with our participants, they weren't taking exogenous ketones. They weren't guzzling MCT oil. Again, these participants had actually been in ketosis for a very long time, so they knew what worked for them. We didn't calorie control. They ate ad libitum. Every participant took blood tests, capillary glucose and ketones 4 times a day, when they woke up, before lunch, before dinner, and before they went to sleep. And so as evenly spread over the day as possible. So each test was no less than 3 hours after a meal. Now, of course, many of them would test after a meal. They were looking at the interactions of the meal, those things. But for the trial, it was these 4 tests that were the most important. And they had to photograph their meters, and they were actively sending it in to the researchers. It was actively live collected, no memory recall. And it was also for auditing purposes. They had to photograph what they were eating. Sky view, hand flat, photograph down, so that we can have a size representation as well. And they did this consistently. Because when it comes to running ketogenic metabolic trials, especially for cancer, you need to know that the adherence, you need to know that, why would you have no findings if they were complying? Why would you have no findings? And often it's because people are measuring only in the morning and they don't know what's happening through the rest of the day. So here, the participants, if you think those 4 tests a day, for 66 days long, they had the ability to have 252 capillary glucose and ketone tests. And as you can see, the compliance was 93.4%. So it was extremely high compliance. So we really knew that these participants, over the course of their awake hours, were absolutely in ketosis, and they were actually in therapeutic levels. In the 2 ketosis phases, it was 1.9, nearly 2. So really, really excellent readings. Breaking it down even more, in terms of the threshold that they're reaching, actually what was really interesting was in P2, phase 2, that was the carbohydrate introduction to suppress ketosis for 21 days. It actually took 6 full days for the participants to be knocked out of ketosis. That's how well adapted they were. And so you can see, even in the phase 2, in some of the participants, they were going above 0.5 quite regularly, and even quite often above 0.3. So these are very, very well adapted, very healthy participants. And again, the purpose is to have a healthy control group, so that when we do trials in other groups, we've got a healthy control group to compare against, being in ketosis, out of ketosis, and back into ketosis. So here's some summary on them, on their anthropometrics. And going to P2, they did end up gaining some weight. About half of it was water weight and half of it was fat weight, of which they lost all of it when they ended up, at the end of the whole trial, back into ketosis. So that all came off. Their blood pressure regulated excellently. And here, just looking at some data of the RQ, the respiratory quotient, essentially, they were super healthy in all phases, as you can see. Specifically, the RQ was really, really low in both the ketosis phases. And that's really interesting because it was below 0.7, which means that some of these ketones, a lot of the ketones that they're producing, are not being used as an energy substrate. And we know that ketones do other things. We know they act as antioxidants. They act as gene regulators. So they do a lot more of other things. And, some people will say, well, maybe they're breathing them out, urinating them out. These these participants, especially in phase 1, they're actually completely weight stable. So they're not on a forever weight loss, So these ketones were obviously being used for different things. It's important to point out that the calorie consumption remained the same between the phases. Because a lot of people might say, yeah, but all those changes might be because you had increased calorie consumption. And we know that chronic consumption of carbohydrates can increase, or rather decrease satiety and drive hunger signals. But these participants, they're incredibly sensitive to the satiety signals. But, again, it was a completely ad libitum. No one was counting calories at all. And it turned out the calories were the same. And even the saturated fat intake, there was no statistical significance in the change. It really was carbohydrates were the difference between the phases. So here's starting now some of the summary of the data. The main markers that we were really interested in this trial was insulin and IGF-1, and that's what the trial was actually powered for, looking at changes of insulin and IGF-1. Because based on the literature, the other growth factors and all the other changes are downstream of insulin and IGF-1. So, as you can see, there were massive significant changes, as well as in other markers like thyroid, which we'll get into as well. First, I want to address HOMA-IR, which is, typically only ever measured for type 2 diabetes and obesity. And I think this is a big shame. I think that, more people should ask their doctors to measure their HOMA-IR, which essentially is a calculation of your fasting insulin and fasting glucose. And it's about 65 to 75% accurate. And the reason being for that is, when you went in to go and have your test, insulin has this oscillatory pattern. It's a 24-hour oscillatory pattern. And then it has an ultradian pattern, which is about 180 minutes, and then this pulsatile pattern. So it might be at the time that you go for the test that your insulin happens to be at the bottom of the bottom of the bottom of that pattern, and you might even have be a low glucose moment. So you'd have this false negative of a low HOMA-IR. So just keep that in mind. But there are other markers that you can measure at the same time that would tell you whether that happened for you. But HOMA-IR in general is a good way to know because the higher the HOMA-IR is indicative of mitochondrial dysfunction. It is an insulin resistance index. And it's associated, HOMA-IR is associated with increased risk of cancer and worsening prognosis. And as you can see, insulin, as it goes up, IGF-1 goes up. They track together, and insulin really drives an increase in IGF-1 production, but also insulin controls the amplification capacity of IGF-1, meaning one molecule of IGF-1 comes along to its receptor and signals, and if insulin is low, then that molecule is going to signal, let's just make up a number for now and just say 100 amplifications inside of the cell. But once insulin comes around, and if insulin is chronically high, it's going to change that amplification from 100 times to 10,000 times. It's like having more speakers inside of a stadium, and it's insulin that actually does that. IGF-1 is an incredibly potent mitogen. Mitogen meaning mitosis, to proliferate, to grow and divide. And it also directly inhibits apoptosis as well via the mitochondrial pathways. So literally the mitochondria, it has this pathway in sciencey terms, BCL2, BAX-BAD, these control apoptosis signaling from the mitochondria, release of cytochrome C from the mitochondria. The mitochondria really are the dominant part inside of the cell that has the kill switch to be able to turn off and commit this controlled healthy cell death in cells that are not good for your body. And IGF-1 as well as insulin, both of them can do this and do this when there's too much of them. And IGF-1 is quite predictive in prognosis with cancer as well. The higher it is, the worse the prognosis. So higher levels of IGF-1 increases risk and also worsens prognosis. I do want to touch on a lot of people saying chronic ketosis is a high stress event, that it's not something you should sustain for a long time. It's going to raise your cortisol, and raise cortisol. Hypercortisolemia is really bad for you. It's going to cause muscle wasting. You hear a lot of people talk about this, that it's really bad for your body to have to make its own glucose. So I don't know how the Maasai are here, and I don't know how the Inuit either survived either, because they would have been making a lot of their own. But the point is, we measured cortisol, and you can see the cortisol levels in our participants were completely normal. There was actually no significant change between the phases. And in the ketosis phases, they actually fell perfectly in the middle of the reference range. So, I think that some people, when they look at cortisol changing, it might be that it's quite a transient time when they're going into ketosis, when they haven't had to rely on their livers to actually supply the glucose load for their body. And that's a sort of period of a stressful event for the body. Just like when you just start going to the gym and you haven't been for years, it's quite a stressful event on your body. But eventually, after a while, your body goes, okay, that's the new norm. And it's no longer stressful for the body. Then we have thyroid. You hear a lot of people say, it's really bad for your thyroid. You're going to have, you're going to suffer a slow, sluggish thyroid. And especially in women, they're discouraged to maintain ketosis. And when you look at the data here, you do see that T3 is lower. But what you don't see is TSH changing, which means they needed less T3. So that's the difference, because people always think, well, their T3 drops. So in essence, what they're really saying is a higher T3 is better. But when you know what T3 actually does, what it's for, your body calls on your thyroid to produce more thyroid hormone, T3, the active form? Because your mitochondria are being damaged, because they need to be replaced. So why would you want to see a higher T3? It means you're actually exhausting and assaulting your mitochondria more. So under a healthy context, low blood glucose, low HOMA-IR, low IGF-1, normal cortisol, then a low T3 is not a problem. It actually means you don't need to be fixing your mitochondria as much, as well as the ketones are actually helping to fix your mitochondria and help maintain them, keep them well as an antioxidant as well. So we then went on to do these oral glucose tolerance tests. So the participants were given 75 grams of glucose in 250 milliliters of water, which they had to drink in 5 minutes. And we tested their blood glucose, ketones, and insulin response over 5 hours. I do not recommend this for cancer patients. I don't recommend it in cancer trials. I think it would be unethical. However, I think that we can modulate this kind of testing mechanism to see individual responses to foods. So being in ketosis, just being in ketosis, you can actually see that the beta-hydroxybutyrate curve, there are these wonderful U curves for the BHB, which you don't see when the participants are in a suppressed ketosis, in a hypoketonemic state. That's the pink flat line that you see on this side. So when they're in therapeutic ketosis, having the carbohydrate, of course, naturally brought the ketones down in the participants. However, it actually didn't knock them completely out of ketosis. And you can see by the 5th hour, the participants were fully back into deep therapeutic ketosis. Now, the way that can be used for cancer patients is, wanting to know how sensitive am I to this particular food, whether it's broccoli, whether it's a different type of meat, which ones am I better with, whether, how detailed do you want to go? Can I have onions? Can I have garlic? Can I have black pepper? All of these sort of things. None of us can go around and say, oh, yes, you can, or oh, no, you can't. There's an individual testing that needs to be done, because also with people with cancers, some have rheumatoid arthritis, some have, other problems that come into that have to be factored into it. And so being able to self-test at home and understand how to do that is really empowering. And then you can tailor what is best for you. Going on from there, we looked at GGT and PAI1. These are inflammatory markers. So GGT, gamma-glutaryltransferase, is essentially, the majority of it is coming out from the liver. It doesn't just come from the liver. And you would have heard of glutathione, it's mega antioxidant. And so glutathione comes in 2 forms. It's reduced form and oxidized form. And so that's the GSH and the GSSG form. And when glutathione is being used up, you get more of the GSSG form. And then this increases the liver's expression of GGT to then recycle the GSSG back to remake glutathione in its reduced form. The problem is that GGT is actually pro-oxidative on itself. So it directly participates in the generation of reactive oxygen species and damages nucleic acids and lipids and increases lipid peroxidation. Let me come back there. The next one is plasminogen activator inhibitor 1. So PAI1 is really sort of typically understood as an antifibrinolytic. So that means to stop the breakdown of blood clots. And that's an important component when understanding cancer, because the more clotty your blood is, the more hypoxic you'll be, right? So that's going to be affecting the hypoxia and then the angiogenesis factor in cancer. But PAI1 actually does a lot more than that. So it affects the infiltration of immune cells. For example, mast cells in glial tumors. It also drives the movement of macrophages. So when you think about metastases, macrophages. PAI1 is actually a very powerful and reliable prognostic marker in cancer. So it's an important one to get measured. So then we move on. Here I'm showing a cluster of growth factors at the top, and then a cluster of inflammatory cytokines at the bottom. Because we do often hear doctors saying, it's inflammation that drives the growth. But actually, if we have a look at here, the cytokines, the classic cytokines, they weren't statistically significant at all. There was no real change. But the growth factors, they changed significantly. So in our cohort, that was a pre-mover. We didn't have the increase in cytokines. And when we look at them more closely, VEGF, EGF, and MCP1, so vascular endothelial growth factor, in tumours they actually have an increase of the receptors, as well as it's typically found to be increased in cancer cells, the actual growth factor in the bloodstream. And vascular endothelial growth factor promotes, again, growth, proliferation, inhibits apoptosis, controlled cell death. And another thing with vascular endothelial growth factor is actually insulin stimulates pericytes to make more vascular endothelial growth factor. And pericytes are involved in angiogenesis. They actually drive the endothelial cells and increase blood vessel supply to cancer cells. Additionally, VEGF, interestingly, actually affects your bone cells. So it causes osteoclasts, which are a type of bone cells that were originally monocytes from the immune system, to resorb, which is to break down bone tissue, which actually creates a more favorable environment for tumor cells to colonize. And this is something inside of cancer, obviously, with regards to tumor metastases commonly coming to the bones. Then the next one is EGF, epithelial growth factor. Epidermal growth factor. So commonly people will have their cancers tested, are they epidermal growth factor receptor positive? And if they are, then there are certain drugs that are given to either block, usually to try and block the receptor, but they're not thinking about the actual epidermal growth factor in the bloodstream, which, by the way, can actually activate the vascular endothelial growth factor receptors. And the vascular endothelial growth factor can activate the epidermal growth factor receptor. They can cross-activate each other. Then you have MCP1, monocyte chemotactic protein. And as its word suggests, is chemotactic and monocytes. So monocytes, to have them move, and it's involved in migration of cells. And interestingly, again, insulin causes your bone cells, your osteoblasts and osteocytes, to actually secrete MCP1. That then attracts monocytes, turns them into osteoclasts, and at the same time, VEGF is telling the osteoclasts to resorb your bone and create a more hospitable environment for tumor cell colonization. And with a lot of the drugs that are inhibiting these receptors, or inhibiting the actual growth factors, if you inhibit the receptor and the growth factor of one, EGFR, for example, it's not taking into account that VEGF can activate that receptor. IGF can activate the EGFR receptor. Insulin can activate it. So if you don't deal with the upstream factor, then of course the drugs are not going to be that effective, because they'll just get overridden. And then coming to leptin. Leptin is actually involved in angiogenesis, and it also inhibits apoptosis as well. It increases VEGF stimulation to make more of it, and it also increases and upregulates the epidermal growth factor receptor as well. So leptin's highly involved. And in actual fact, it's quite good for prognosis as well. Leptin also increases estrogen synthesis, and it increases estrogen receptor expression, and it can trigger estrogen receptors without estrogen. So if you think about it, with breast cancer as an example, when you're given something to stop you from making estrogen, well, leptin's going to signal those receptors anyway. So looking at leptin, how strongly it responds to being in ketosis, ketogenic metabolic therapy, along with all those other markers that I mentioned, what drug can do all of that, right? There's no other drug that can target all of those and reduce those growth factors that are all impacting cell growth and division, proliferation and inhibition of apoptosis. all via the mitochondria. And so that's how powerful this treatment, this therapy, this lifestyle choice can be. And so we did this control group, hopefully for the benefit of future research, that they'll be able to use that as their standard of, in terms of the testing, the compliance and things like that. And this is just a summary of what's going on in the bloodstream at the top level, and then what's going on inside of the cells. And on the sides, the growth factors that I've listed, the ones that go up, the ones that go down, that I would encourage researchers at least, and clinicians, to start measuring these growth factors. They're expensive at the moment, but if more people do it, it will drive the price down. And that's if anybody wants to sort of, again, nerd out on the intracellular signaling that goes on. We also developed a sort of categorization, a schematic, to understand people in their metabolic phenotypes, because when you read blood test results, you have to understand them in context. Again, as I mentioned, a low T3 in a person who is in therapeutic ketosis is likely perfectly healthy. And then just a summary in terms of metabolic health, we mentioned metabolic dysregulation. A lot of the time, it's like if you fail to reach three of these five that are listed over there, then you're technically metabolically unwell. And in our trial, we wanted to show, even when our participants did come out of ketosis, they were an incredibly healthy cohort. And so they actually still stayed very, very healthy. But that's the representation of if you were living, like a saint all year, and you took a 3-week Christmas holiday, it's not going to kill you. Or rather, if we think about our ancestors, if they did see all the fruits and berries and maybe some honey in summer or at the end of summer, then they would gorge and binge, because humans were opportunistic. But we weren't doing it 365 days a year. And I do want to come back to saying about our research and funding. Our research is 100% philanthropically funded. So we provide consultations as biochemistry and nutritionists in our team as well. And all the consultations that we provide, the fee for it is 100% donation to our research, of which 0 goes to administration fees. So this enables us to remain completely independent. So if you can help, if you can tell other people, everything goes a long way, and in terms of everything that we are all fighting for. And thank you very much.